Hi there. Today, we are going to walk through a realistic DevOps interview focused on messaging systems and event streams. These are the technologies that keep modern distributed systems running smoothly when data needs to move quickly, reliably, and at large scale. I will ask you questions that explore how you think, how you debug, and how you make trade-offs in real production environments. If you want the best experience, pause after each question and try answering out loud before listening to the sample response. And if this helps you prepare, subscribe so you do not miss the next interview session. Let's begin with a few behavioral questions to understand how you work with asynchronous systems, queues, and event-based architectures. Tell me about a time you introduced a message queue or event stream to solve a performance or reliability issue. What was happening and what was the outcome? A strong answer might sound like this. We had a service that was doing heavy processing in real time. During peak hours, the workload overwhelmed the API and caused user-facing delays. Instead of processing everything synchronously, I introduced a queue so the API could accept requests quickly and let workers handle the heavy lifting in the background. This let us smooth out traffic spikes and reduce latency. Over time, we scaled the workers and added monitoring on queue depth, which made the whole system more predictable. It taught me how effective decoupling can be when dealing with uneven workloads. Next question. Describe a situation where a messaging system caused problems instead of solving them. What did you learn? A solid answer could be We had a queue that was used by multiple services. One team deployed a new feature that produced many more messages than before, and the queue started filling faster than the consumers could process. We did not have good visibility into the backlog at the time, so the problem grew quietly. Eventually, the delay became noticeable to users. I learned that queues need strong observability, clear ownership, and consistent capacity planning. Without those, they can hide problems instead of exposing them. Next behavioral question. Tell me about a time when ordering of events mattered and created unexpected bugs. A thoughtful answer would be, we had an event-driven system where user changes were published as events. During high load, events sometimes arrived out of order at a downstream consumer. For example, a delete event could arrive before an update event. This caused inconsistent state. We fixed it by adding version numbers and ensuring consumers validated event order before applying changes. It taught me that event streams do not always guarantee order, and consumers must be designed defensively. Next question. Explain a time when you had to choose between at least once and at most once delivery semantics. What did you prioritize? A mature answer might be, in one project, we processed financial transactions. Duplicates were unacceptable, so at most once delivery was preferred, even if it meant occasionally dropping a message in rare cases. In a different system, we were indexing logs for search. Losing a message was worse than processing it twice, so we chose at least once delivery and made the consumer idempotent. The lesson was that delivery semantics need to align with the business outcome, not just technical preference. Final behavioral warm-up. Tell me about a debugging session involving a messaging system that took longer than expected. What made it difficult? A realistic answer could be, we were debugging an issue in a Kafka consumer group that occasionally lagged behind. It took time because the problem was a combination of slow consumers, uneven partition distribution, and a large spike in message size. None of those were obvious at first. We had to look at consumer lag over time, partition assignments, and the actual payloads. It taught me that messaging systems require end-to-end visibility, not just CPU and memory metrics. Now let's move into the first half of the technical questions. Explain the difference between a queue and an event stream. When would you choose each? A clear answer might be, a queue is designed for point-to-point communication where each message is processed once by one consumer. It is great for jobs, tasks, and asynchronous workloads. An event stream keeps a log of events that multiple consumers can read at their own pace. It is ideal for analytics, real-time processing, and systems that need replayability. I choose a queue when I care about distributing work and a stream when I care about preserving history and allowing multiple consumers. Next scenario. Your consumers are falling behind on processing messages. Backlog is growing and latency is increasing. How do you approach diagnosing this? A strong answer could be, I start by checking whether consumer throughput has changed. If each message is taking longer to process, that could be the issue. Then I look at message size, since large payloads slow both network and storage. I also check partition distribution to see if some consumers are overloaded while others sit idle. Finally, I look for upstream spikes or retries that inflate volume. Once I understand the bottleneck, I can scale consumers, optimize the processing logic, or rebalance partitions. Next question. What happens if a consumer in a messaging system dies halfway through processing a message? How do different systems handle this? A thoughtful answer might be, in many systems, if a consumer dies before acknowledging the message goes back to the queue or becomes visible again for another consumer to process. In event streams, the message is not lost because the stream keeps all events until retention expires. The consumer simply resumes from its last committed offset. The key is understanding the acknowledgement model and ensuring idempotency so reprocessing is safe. Next scenario, you have a service that publishes events to Kafka. Occasionally, the producer fails to publish, but the application does not notice. What is your first reaction? A mature answer would sound like, this tells me the producer is not properly checking for errors or timeouts. Kafka producers should handle retries, acknowledgement requirements, and delivery guarantees. I examine the producer configuration for ACK settings, retry logic, and timeout thresholds. Then I look at metrics to see if brokers are overloaded. The first priority is ensuring the producer does not silently drop messages. Reliable error handling is essential. Next question. Your system uses a queue to handle user uploads. Suddenly the queue depth spikes, but the workers appear healthy and CPU usage is low. How do you explain this? A solid answer could be, low CPU usage suggests the workers are waiting on something blocking. It could be network latency, slow disk writes, or waiting on an external service. I inspect worker logs, request times, and downstream dependencies. When queues fill up but workers are idle, it usually means the bottleneck is not compute, but I/O or a dependency. Identifying that allows me to focus on the true choke point. Here is the next question. Imagine you have a Kafka topic with 12 partitions and a consumer group with 6 consumers. For some reason, only 2 consumers are doing most of the work and the others are mostly idle. How would you explain this? And what would you do? A strong answer might sound like this. My first thought is that the partitions are not evenly assigned. Kafka guarantees that a partition is consumed by exactly one consumer in a group, but it does not guarantee perfectly even distribution. If the partitions that carry most of the traffic happen to be assigned to only a couple of consumers, those consumers will be overloaded. The next step is to look at the partition-level traffic patterns. Some partitions might be receiving a lot more messages than others because of how keys are distributed. If the keying strategy is skewed, the workload becomes unbalanced. I might change the keying logic to distribute data more evenly. If rebalancing alone does not fix the issue, I might increase partition count or scale consumers further so the load can be spread more effectively. Here is another scenario. Your team processes events from a third-party service. Sometimes the third party sends malformed messages that break your consumers. How do you build resilience so your system does not crash, even when the input is unpredictable? A thoughtful answer would be, I start by making parsing defensive. Instead of assuming the message format is perfect, I validate every field. If something is missing or invalid, I route the message to a dead letter queue. This keeps good messages flowing while isolating the bad ones so we can inspect them later. I also introduce metrics that track error rates per message type, because a sudden spike often indicates an upstream issue. Finally, I add backoff and retry logic around transient failures. The key is to contain the blast radius, so one bad payload does not take down the entire consumer fleet. Next question. Let's talk about exactly once processing. People love the idea, but in practice it can be complicated. If your business team says they need exactly once handling of events, how do you approach that requirement? A mature answer might be, I start by clarifying what they actually mean. Often, they are really asking to avoid duplicate side effects, not literally ensure one read of a message. In many systems, the consumer can be idempotent, so even if an event is processed more than once, the state does not change unexpectedly. If they want strict guarantees, I explain the trade-offs. True exactly once processing requires coordination between the producer, broker, and consumer. It can increase latency and reduce throughput. I walk them through options like using Kafka transactions or building idempotent handlers. The goal is to balance reliability with performance and complexity. Many teams settle on at least once delivery with idempotency because it is simpler and scales better. Let's move to another scenario. Imagine your message queue is backed up because downstream systems are slow. You cannot scale the downstream service easily, and you cannot drop messages. What approach would you take to keep the system stable? A strong answer could be, first, I would slow down the producers by introducing back pressure. If producers keep firing messages at full speed, the queue will grow endlessly. I might reduce batch sizes, apply rate limits, or add retry delays. Next, I would increase consumer parallelism where possible. Even if the downstream service is slow, we might be able to process more messages in parallel. I would also check if we can make processing smarter, like deduping, merging similar operations, or discarding tasks that are now outdated. If none of that is sufficient, I would enable auto-scaling on the consumers so they can expand during heavy load and shrink later. The overall goal is to avoid overwhelming the slowest part of the system. Next question. Your application publishes events to an event bus. After a recent deployment, you realize some events are missing. They were generated but never arrived in the stream. How do you debug this? A realistic answer might sound like, I check the producer code path first. If the deployment changed logic around how events are created or dispatched, that is a likely source of issues. Then, I check the producer configuration for timeouts, buffer sizes, and acknowledgement settings. A misconfigured ACK level can silently lose messages if brokers are slow. I also inspect logs around send failures, flush failures, and retry exhaustion. If everything looks fine on the application side, I move to the broker. I check broker logs for timeouts and throttle events. The key is to trace the entire journey from event creation to event persistence. Most missing events are caused by silent producer failures or misconfigured retry behavior. Next scenario. You have a system that uses both a queue for immediate tasks and a stream for long-term analytics. Suddenly, the same event appears twice in the analytics stream, even though it should be unique. How do you trace the duplication? A thoughtful answer would be, I begin by checking whether the producer sent the event twice. Maybe it retried due to a timeout, but the first attempt actually succeeded. Then I look at the queue consumer that publishes to the stream. If it crashes after publishing, but before acknowledging the queue message, the queue might deliver it again. I also check for batch processing logic that replays data during startup. Sometimes, a replay mechanism triggers incorrectly and duplicates historical events. Once I isolate the source, I ensure idempotency. That might involve adding event IDs, versioning, or dedupe logic in the stream consumer. The overarching goal is to make the system tolerant to retries, because retries are inevitable. Final question of this section. Picture a system with thousands of events per second. Some consumers need real-time data, while others only need near real-time batch updates. How do you architect this so each consumer gets what it needs without overwhelming the system? A solid answer could be, I would separate the consumers by responsibility. Real-time consumers subscribe directly to the event stream and read events as soon as they are produced. Batch consumers do not need to read every event immediately. They might use a smaller consumer group, or read from a compacted topic, or even pull snapshots from a data lake fed by the stream. I would also enable partitioning so consumers can scale independently. This design avoids forcing all consumers into the same performance model and keeps the system cost-efficient and flexible. Let's move into the pressure section. These questions are intentionally ambiguous, and I want you to think through how you would act when the situation isn't clean, the data isn't clear, and decisions still need to be made. Here is the first scenario. You discover that your event stream has been lagging for several hours. The business teams rely on near real-time data, and leadership wants answers immediately. You do not yet know the root cause. What do you do first? A strong response could sound like this. Wrong? I would start by acknowledging the issue transparently and setting expectations. I let stakeholders know that we are investigating and will share updates as we learn more. Then I check the critical metrics: consumer lag, broker load, network throughput, and partition health. If the system is running but slow, I look at scaling the consumers or clearing backlog in a controlled way. I avoid rushing into drastic changes until I know whether the slowdown is caused by traffic spikes, consumer failures, or broker issues. My goal is to stabilize the system first, communicate clearly, and avoid adding risk while visibility is still limited. Here's the next one. Imagine you receive conflicting information. One team insists events are missing. Another team says everything is working as expected. Logs and metrics are noisy and inconclusive. How do you navigate this without escalating unnecessary panic? A thoughtful answer might be, I step back and try to isolate what each team is actually seeing. Missing events could be a consumer side issue, not a producer problem. Or maybe the events arrived but were filtered out by new logic. I ask for concrete examples, specific event IDs, timestamps, and expected behaviors. Once I have that, I trace those events through the pipeline. I avoid assuming that the first complaint is the true root cause. I also keep communication calm, factual, and focused on what we know versus what we do not know. The worst thing in this situation is to guess. My role is to create clarity where there is confusion. Here's another pressure scenario. Your consumers are falling behind. You could scale them up aggressively, but you know the downstream database is already near its limit. If you scale too fast, you might cause an outage. If you do nothing, latency keeps growing. How do you decide? A mature answer would be, I start by protecting the downstream system. If the database goes down, everything stops. So instead of scaling blindly, I reduce throughput intentionally. I might add back pressure or temporarily slow producers until the database recovers. Then I look for opportunities to process messages more efficiently, like batching writes or compressing payloads. If we need more capacity, I escalate that to the team responsible for the database. My decision-making here is simple. I would rather be slow and consistent than fast and broken. The business can tolerate delays better than data corruption. Here is the final pressure question. A critical event stream is failing sporadically. Sometimes messages arrive instantly. Sometimes they take minutes. Logs do not show clear errors. You can't reproduce the issue locally. You only know something is wrong, but you don't know where. How do you lead the investigation? A well-grounded answer could be, I start by mapping the entire path of the message. Producer, network, brokers, partitions, and consumers. Then I look for patterns. Does the delay only happen under high load? Is it tied to specific partitions? Is it correlated with broker GC cycles or network spikes? I also enable additional tracing to tag events end to end. When you can't reproduce locally, you rely on observing the system in its natural state. I would also bring in people who manage the parts of the system I don't have full visibility into. The investigation might take time, so I maintain communication with stakeholders and provide regular updates. The key is to avoid tunnel vision and treat it like a distributed systems mystery that requires patience and systematic thinking. That wraps up today's interview. Take a moment and think about how you answered these questions. Messaging issues and event stream failures are some of the hardest problems in distributed systems, and how you think under pressure is often more important than the specific tools you know. Which question challenged you the most? Was it the lagging consumer scenario, or the conflicting information, or maybe deciding between scaling and protecting the downstream system? Let me know in the comments, and if you want the next interview in this series, make sure you subscribe so you don't miss it. Thanks for practicing, and I'll see you in the next session.